for those kids that cannot make it to the session because they're in school or wherever else they are. Some are working, some are in school. All right, today is week number 3. Crazy how it's week 3 already. We are going to review a little bit before we get into this week's material. First thing, what is a limit? In your own words, what is a limit? And you can use your microphone if you want to, or use the chat box. But when you think of a limit, what do you think of? What is a limit? What is your definition? Okay, the intended limit of a function. I would say you cannot use the word limit to define what a limit is. I would say the intended height of a function. That would be my definition of what a limit is. It is the intended height of a function. How high is a function going to go? All right, so let's review a little bit of what we went through last week. This is an awesome problem. This is a type of problem where you can tell if a student understands a lot about limits, left-hand limits, right-hand limits, what a limit is. So part A, it asks us, what is the limit as x approaches -1 from the left-hand side? Okay, so what is the limit as x approaches -1 from the left-hand side? What would you guys say that the limit would be there? 2 is absolutely correct. Very good. What is the limit as x approaches -1 from the right-hand side? +2 is correct. What is the limit as x approaches -1? That is also 2. Now let's put an extra problem in here. Let me ask you, I gotta get my marker to work. What if I asked you this question? What does f of -1 equal? It's not a limit, it's just a regular question. What is f of -1 is equal to 1? That is absolutely correct because that is where it's defined. Very good. What is the limit, part D, what is the limit as x approaches -4? Does not exist. That is correct. How about the limit as x approaches +4? Does not exist. Very nice. You guys understand your limits through graphing. Very nice. Love it. Then we went on and we found limits using algebra. Okay. You may use a graphing calculator to solve the following problem. No, I don't want you to use a graphing calculator. I just took this off an AP test, and that was one of the graphing calculator sections. But when you're looking for a limit, there's a couple rules. The first rule is just plug the value in. So I'm going to plug 3 in here. So that's going to give me, oops, I'm going to turn my marker back on. 3 squared minus 3 minus 6. So that's 9 minus 9, so that's 0 on the top. If I put 3 on the bottom, 3 minus 3, that's 0. So I have 0 over 0. Can't do it. Okay? I can't do it the way it sits, but I'm going to factor the top and bottom. So the top factors to x minus 3x plus 2. The bottom doesn't factor. It's still just x minus 3. However, I can simplify. Now I have x plus 2. So now if I plug 3 in here, 3 plus 2 is 5. So my limit would be 5. All right. Do you guys know what happens to a graph when, let me ask you a different question. If I asked you to graph this, f of x is equal to x squared minus x minus 6 over x minus 3. Could you guys graph that without a graphing calculator? Could you just graph that thing out? No problems, no calculator, nothing, no Desmos. Are you able to graph that? And if you can't, that's perfectly fine. A lot of kids can't graph this. Probably not. let me ask you another question. Can you graph this? If I asked you to graph y is equal to x plus 2, could you do that? Yes? Okay. These graphs are exactly the same. These two graphs are exactly the same, except when x equals 3. When x equals 3, there is a hole in the graph. Why is there a hole? Because the top and bottom crossed out. When the top and bottom both cross off, whatever makes it equal to 0 puts a hole in the graph. So if I had to graph this function out, it is exactly the same as this, x plus 2. So I would just go up to 2, 1, 2, and then at x equals 3, 1, 2, 3, when I graph that, when I got to 3, I would just put a hole there and continue on. That is a graph of this function right here. Pretty awesome, hey? So that is how we, sometimes it's, when you're graphing, it's like, oh, this thing looks way too hard. Well, you simplify it down, it's just a simple linear function. And if the top function and the bottom function, if they both are the same and they cross off, then whatever makes it equal to 0 is going to be a hole in your graph. That's what causes the hole. In this problem, it says the limit as x approaches 2 from the right-hand side. Well, the first thing we have to do is we have to figure out which one of these functions are we going to use. Are we going to use this one? Oops. It's kind of strange this year. Every time you change a page, you have to turn your marker back on. Are we going to use this function or this function? This is a piecewise function. But it says that we're supposed to use this one when x is greater than or equal to 2. Well, it's asking me to find the limit as x approaches 2 from the right. Well, that would mean I'm coming from the right-hand side. That would mean the x is greater than or equal to 2. So I would use this function right here, and I would just plug 2 in here. So my answer would just be 5/3. That's it. Okay, so you have to understand what a piecewise function is in order to understand which value you're supposed to plug in there. All right. Evaluate each one of these using algebraic methods. Well, okay. Being able to factor, a lot of kids, they say, Mr. Shanklin, calculus is too hard. And it's like, calc is usually not the problem. Calculus is not difficult as long as you have the skills. And what type of skills do you need in calculus? Factoring is one of the hugest skills that you're going to need this year. You're going to be factoring a lot of things. When we do limits, when we do derivatives, when we do a lot of different things, factoring is one of those skills that you need. Okay, so if you're good at factoring, you'll probably be okay. So now this problem here, if I'm going to factor, I look at this and I'm saying, okay, what two numbers multiply to give me 5 but add up to -6? Well, that's going to be x minus 5, x minus 1, because -5 and -1 add up to -6. If I multiply them, I get +5. So now if I factor the bottom, what two numbers multiply to -12 but add up to 7? So that's going to be x. Oh, let's see here. Does that factor? I'm drawing a blank. 4 and 3? Yeah, but it has to multiply to be -12. So if you did +4 times +3, you get +12. It adds up to 7, but it's not negative. So I'm going to say that this does not factor. All right, now I did not follow my own rules. Usually when I see a problem like this, I always think, oh, I got to factor it first. But I didn't plug the number in to see if it works, first of all. So if I put 3 in here, 3 squared minus 6 times 3, well, that's 18 plus 5. So 3 squared is 9 minus 18 plus 5. So that's -9. So that's -4 on top. Now if I plug 3 in the bottom, so that's 9 plus 21. Oh, yeah. Substitution works in this problem. I didn't have to factor it. Substitution worked right away. So that's 30 minus 12. 30 minus 12 is 18. So I would say it's negative 2/9 is my limit. Oh boy. See, that's why last week we learned that substitution was the first method that you're going to use when trying to find a limit. You're just going to substitute the number in. And in this problem, substitution worked. Now in this problem, if I put 2 in here, 2 squared is 4 minus 8 minus 4. So that's, 4 minus 8 is negative 4. So that's negative 8 on the bottom. And on top, I end up with 4 plus 2, which is 6. So substitution worked for both of these problems. I didn't have to do any factoring at all. To tell you the truth, if you try to factor, your answer is not going to be right if substitution works. So please do not factor if you don't have to. All right. These problems were on AP test before. Okay. I am going to let you guys try both of them. Okay. When you get your answers, just throw them in the chat box and we'll see see if you get the answers correct. Okay. So give it a shot, see what you get. All right, now the top one, I'm looking at this problem. And you guys don't have the skills to solve it yet. This is a type of problem where you plug it in, you get 0 over, no, you can plug it in. Number 1 can be solved. I thought I was gonna have to use L'Hopital's formula, but you don't have to. Number 1, if you plugged it in, you get 4 minus 4. Which is equal to 0. But then on the bottom, you get 4 plus 4, which equals 8. This is an answer. It's when the bottom is 0 that you have to do something different. But the bottom is 8. This is an answer. 0 divided by 8 is 0. So my answer is 0 for this problem. Okay? Because substitution does work on this problem. The top can be 0. Okay, it's when the bottom is 0. That's when we have problems because you can't divide by 0. It's one of those mathematical things that you can't do. So, but this one, the bottom is 8, and it absolutely does work. So the answer should be B there. Now, you said the answer to the next one, answer is going to be C. So in this problem, if I plugged in 3, I get 3 minus 3, which is 0. If I put 3 in here, 9 minus 6, that's 0. Okay, so I have to do something else. So I'm going to factor the bottom. Well, if I factor the bottom, I think it factors x minus 3, x plus 1. X minus 3 is cross off, so I'm left with 1 over x plus 1. Now if I plug it in, I do end up with 1 over 4. You are absolutely correct. Very nice. That is the correct answer. All right. Isabel, do these make sense? Awesome. All right. Now, this week on the PACE chart, you should see that we have AP classroom videos. Have you guys watched these videos at all? These AP classroom videos? they're not bad. I mean, sometimes they do talk a lot, okay, but they're not bad. And then the Khan Academy, and then this week you have 2 assessments. You have 3 assessments: continuity, removable discontinuity, and continuity again. I think 2 out of the 3 are multiple choice, if I'm not mistaken. All right, so that's what our goal is for this week. Is we can define continuity at any point, and I can find and remove discontinuities. What makes a function continuous? All right, we got a short little video here. Shouldn't take this one. I think is really short. Let's see here.
Relies heavily upon the existence of what's called continuous functions. In fact, most of your important theorems include a prerequisite that any function in question must be continuous before you can even think about applying the theorem. For example, the intermediate value theorem, which we'll also learn in this chapter, requires that the function be continuous. Well, in theory, continuous functions are predictable functions. They have no undefined points, no breaks, no holes, no jumps in the graph. But enough talk. Let's take a look at some pretty pictures. Now this function f is continuous, but these g, h, and I, they're not continuous. Each of them in fact is continuous for a different reason at the x value of x equals c. Now this one on g, you've got a little hole in the graph. That's called point discontinuity. Over here on h, you've got a vertical axis that breaks the graph. Now this is called infinite discontinuity. And finally here on graph
good grammar and spelling
are
are
important.
important.
Just snaps in the middle. And that's called jump discontinuity. Now how can you judge just by looking at the graph of a function if it's continuous or not? Well, a continuous function makes a good bridge. Now see, if I drive across the graph of f, it holds up nicely. Whereas if I try to drive across the graphs of the other functions, I might either fall through or fall off. So, continuous functions are predictable. But what does that mean? Well, it means two big things. One, no breaks. Well, we already know that breaks occur in functions when no limit exists there. Therefore, for a function to be continuous, it must have a limit at every x in its domain. Secondly, no holes. Continuous functions must be defined everywhere in their domain. Mathematically now, we say that continuous functions have this property. For every x equals c in their domain, the limit as x approaches c of f of x is equal to f of c. In other words, not only does the limit exist at every point, but the height the function reaches for every x matches the limit. How can you tell this happens? It seems pretty complicated. It's actually easy. If you can evaluate any limit on f of x using only the substitution method, then the function is continuous. And that's all there is to it. Now that you understand what it means for a function to be continuous, we can look at our first major continuity theorem, the intermediate value theorem. Now before we get into explaining what it means, let's take a look at exactly what it says.
All right. Sorry about that. The intermediate value theorem comes a little bit later. We want to talk about continuous functions first. All right, so I got to get back to my files here. All right, so I want to go back to this problem that we worked on in the beginning of class. Is this function continuous at -1? Okay. No, absolutely not. There's a hole, and we could not draw a pen. Now, this is where the fundamental theorem comes into play. And this is where, you know, it didn't make sense to me a long time ago, and it's like, oh, this is so simple. What they're really saying is the limit as x approaches -1 from the left, we said that was 2, right? And then we said the limit as x approaches -1 from the right was 2. But then, in order for it to be continuous, f of -1 has to equal 2. That dot has to be right here. If f of -1 was equal to 2, then this would be a continuous function, because from the left it equaled 2, from the right it equaled 2, and the function is defined at 2. That would make it a continuous function. Those are the three things that have to be true in order for something to be a continuous function. The left-hand and right-hand limit must equal itself, and the function must have the same value as the limits as they come from the left and right. And that means there would not be any holes there. Okay, so that is the official definition of a continuous function. Now, you're going to find today's stuff is fairly easy to do. What type of discontinuities are there? Well, we have, this is called an asymptotic discontinuity. Some books call it, you know, a jump to, no, they wouldn't call this a jump discontinuity. Usually we just call it a vertical discontinuity because there's a vertical line here. Then we have what is called a point discontinuity. So if you have a point here, if there's a point out of there, we call it a point discontinuity. We have what is called a jump discontinuity. So if your graph stops and starts someplace else, we call it a jump discontinuity. So this is the Khan Academy kind of stuff that they would give you. It says this is a graph of a function. Dashed lines represent asymptotes. So this is an asymptote right here, vertical asymptote. Select the x values at which f has a jump discontinuity. Okay, so in the first graph, where does the graph have a jump discontinuity? What x value? X equals, oh, not 4. 4 would be a vertical discontinuity or discontinuous one. A jump discontinuity means that it jumps from one point. You've got a jump here where you'd have to, if you were, you know, walking on this line, you'd have to jump up to get to the next point here. So this is a jump discontinuity. We usually call this a vertical discontinuity when you have a vertical line there. Okay. Now the second graph, it says select the x values at which h has a removable discontinuity. So a point discontinuity and a removable discontinuity are a little different. A removable discontinuity means that you have an open dot, but you have the point is going to be there. We don't usually make the distinction. We usually just say a point discontinuity, but Khan Academy revolves around removable discontinuities. So you're removing the point and you're putting it here. I mean, I would consider these, well, this is a jump discontinuity here, and this is a jump discontinuity here also, but we do have point discontinuity also because there's a hole in the graph. So whenever there's a hole, we call it a point discontinuity or a removable. Either one makes no difference. I give credit for both. Here's the definition for continuity at a point, and it's exactly what I just said before. You have to, the limit from the right and the limit from the left have to be the same, and then they have to equal the same value. Now, this is what used to drive me crazy as a student. You would read this, and it's like, what the heck are they trying to say here? I would always have a difficult time, but when I can see the graph, it's like, okay, the left-hand limit, the right-hand limit have to be the same, and then the value at that point has to be the same as the limit. I mean, they always use the x's and the a's and all that, and just like, kind of makes me dizzy sometimes. All right. Is G continuous at x equals 2? Now, this is where being able to graph this week is going to come in very handy. Okay, I'm pretty good at graphing. We've been going over this in my Algebra 2 class for the last couple of weeks about graphing transformations. This graph here, this whole function here is called a piecewise function. Okay, why is it called a piecewise function? Because there's two pieces to the graph. There's a piece that you graph when x is less than or equal to 2, and there's a piece that you graph when x is greater than 2. So it's called a piecewise function. You have two pieces. The first piece, when x is less than 2, so I usually, when I do these piecewise functions, I usually draw a lot of stuff on there. So this is negative, or this is 2, so I know that I'm going to have one graph over here and I'm going to have one graph over here. My first graph is x minus 2 squared. Well, that is a parabola shifted 2 places to the right. So 2 places to the right. So my parabola would look like, I don't know if I want to, so my parabola is only, you're only going to see the left-hand side, right? Because it was shifted 2 places over to the right, but x is less than 2, so I don't want to graph anything over here. Now the second graph, I'm going to rewrite this as negative x squared plus 2. So what really happens in this graph is it's shifted up 2 places, 1, 2, but then it's a parabola that opens down. So it's going to open down, but guess what? I'll do this in blue. So it's going to look something like this. It's going to open down like this. But you're not going to see this part here. Okay, so I'm going to erase it. I'm going to see if I can erase it. This is going to be a little interesting. So I'm going to erase this part here because you don't see this part. Because you're only going to graph, you shouldn't see this part either. So this is basically what your graph looks like. Now, it looks like they're connected there. It looks like it's a continuous function, doesn't it? Now, I'm going to check and see if it is a continuous function. And the way I do that, and another way of doing these problems is you don't have to graph them out. I mean, that's just the way I do it because I'm more of a visual learner. I could just plug 2 in here. 2 minus 2 is 0. 0 squared is 0. So at 2, it's equal to 0. This graph is equal to 0. Now, if I put 2 in here, this is going to be 2 minus 4, which is negative 2. So this graph, oh, no, I did this right. I just, this should be at 2, it should be way down here. It should be at negative 4. So my graph, I was just freehanding it. So my graph should be way down here. This should be the part of the graph that you should see. It does not connect at all. And I can tell that just by plugging the number in. If I plug 2 in here, 2 minus 2 is 0, 0 squared. So 2, 0 is a point on this graph. That's this point right here. And then if I put 2 in here, 2 squared is 4. 2 minus 4 is negative 2. So 2 negative, oh, was that negative 2? So 2 negative 2, that should be this point right down here. They don't connect. They're not the same point. In order for it to be a continuous function, these 2 points have to be exactly the same. The x values and the y values have to be exactly the same. They're not. So my graph is going to look more like this than what I had in the beginning because I was just freehand sketching it. So your answer should be no, this is not continuous. Now, if it asks the next question, the next logical question I would ask would be, what type of discontinuity is it? And hopefully you would be able to say, oh, that's jump discontinuity. Exactly. So that is how some of the problems are set up tonight. They'll ask you if it's continuous or not, and it might ask you what type of discontinuity is it. Continuity, a function is said to be continuous on an interval when the function is defined at every point on that interval and undergoes no interruptions, jumps or breaks. If some function f of x satisfies these criteria, then we say that it is continuous on an interval. Now, some functions are continuous everywhere. Some are continuous just on one interval and not on another interval. So this problem right here, it says removing discontinuity. Okay. So in this problem, it wants you to make this a continuous function. Okay. So you have to find the value for k that fills it in. So if I'm looking at this problem, thing I'm thinking about is this graph probably has a hole in it. This graph probably has a hole in it. So how am I going to find what the hole is? Well, I'm going to factor. So I've got x plus 3, x plus 2 on top. Then on the bottom, I have x plus 3, they cross off. So at x equals -3, I know there is a hole in the graph, and I know that the graph looks like this. So if I graphed y plus 2, I know that that graph looks like this, but at -3, there's a hole. Okay, now they want me to make this continuous. They want this to be a continuous function. So I have to fill this hole in. Okay, what value goes there? What value goes? What value would k be in order to fill in that hole? -1 is correct. You're absolutely right. Because if you put -3 into my function, my graph, y is equal to x plus 2, if I put that was a 2 here. If I put -3 in there, -3 plus 2 is -1. So that means the hole, this hole is at -3, -1. So in order to fill that hole in, k would have to be -1. I love these problems. They're pretty amazing. They're pretty cool. All right. For this function, and this is another multiple choice problem off an AP test, it says, let f be the function defined by the following. Sine of x when x is less than 0. X squared when x is between 0 and 1. 2 minus x when x is greater than 1, less than 2. And x minus 3 when x is greater than 2. Holy cow. For what values of x is f not continuous? All right. Well, again, I'm just going to graph this thing out. Now, I would not suggest that you guys graph this thing out, but I know that the sine graph, it looks like this, doesn't it? But it says that it's a sine when x is less than 0, so it's going to go this way. Okay, so I have to get rid of that other part because this is not part of my graph. So I'm just going to get rid of that. Let me get a marker here that I can get rid of that. Okay, so now I have the sine of x when x is less than 0. I have like 1/4 of my graph done, which isn't a lot. But I do know that this should be an open dot here, right? At 0. Then I want to graph x squared when it's between 1. So I do know that this is a parabola, and that parabola is going to be opening up. So I know that this is going to go, and it's between 0 and 1. So it's going to go like this. And this point right here is an open dot. But this dot just got filled up, right? Because this is when x is less than or equal to 0, so it fills it up. This one's open. And this point here is 1, 1, because if you put 1 in there, 1 squared, so this is 1, 1. Then I'm going to graph between 1 and 2. I'm really making this difficult on me. Between 1 and 2, I'm going to graph 2 minus x, which is really y is equal to -x plus 2. So if I graph that, -x plus 2, so I'm going to start up here at 2, 1, 2, and I'm going to come down 1 over 1, so it's going to go like this. Something like that. And I'm only going to graph that between 1 and 2, so only this part right here is going to be graphed. So again, I'm just going to take my marker and I'm going to erase what isn't supposed to be graphed. Okay, so I'm going to erase this, and I'm going to erase this. And where did that end up? I'm at the end of 2. So I'm looking at this thing thinking, okay, this is going to be an open dot here, but where did it end up? Well, if I put 2 in there, 2 minus 2 is 0. So this point here is 2, 0. Okay, so there's my graph so far. And then at the very end, I've got x minus 3. So I go down 1, 2, 3, and then my graph is going to go That's going to hit a -1. So my graph is going to look something like this, but then it's going to be solid from here. All right, so again, I'm going to erase what I don't need, and that would be all of this. All right, so there's my graph. Kind of a weird looking graph, but now that I have my graph, it's pretty easy to tell where it's not continuous. It is not continuous at x equals 2 because there is a jump discontinuity there. I can see the jump discontinuity. It's not matching up. Now, if they ask me to make it a continuous function, there's no way I could do that. The only time you can make it a continuous function is if there was a hole. Jump discontinuities, I mean, I could shift the graph up, but that would be way beyond what we're dealing with. So that now, what is another way I could have done this problem? Well, instead of graphing it out, which probably is not the easiest thing to do, you can just check the values. So for example, if I put 0 in here, I know the sign of 0 is 0. So this point would be 0, 0. And then here, I would put 0 into x squared, which would give me 0. And then if I put 1 in there, I get 1. So I got 0, 0, and 1, 1. So it looks like this matches up. This obviously goes to this next one. So again, I could put 1 in there. 2 minus 1 is 1, so I have 1, 1 as a point. And if I put 2 in there, 2 minus 2 is 0. So, all right. So these match up, these match up. And then if I put 2 in here, I'd have 2 comma -1. Well, these two don't match up. So that there is a place where there's a jump discontinuity there. So that's probably the easiest way of doing those problems, is by just plugging the points in. But you obviously can graph it out if you want to. All right. Uh-oh, that was the last slide for today. This week is a fairly easy week. It's just continuity, trying to find if something is a continuous function or not. Awesome. All right, that was it for this week. If you have any questions, you can ask them now. We still have like 20 minutes if you want. If you have any questions, I can stick around and answer anything you have. I mean, calculus starts off fairly easy. It does get harder when we get into derivatives. Things will get a little bit tougher, but right now it should be okay. Any questions? If not, you guys are free to go, and hopefully we'll see you back next week, same time, same place. Awesome. Bye.